because there are some nice graphs that play a role in this subject. So the first thing is just to talk about mechanics. And what one has is a concept of a Hamilton system. And a Hamilton system of n degrees of freedom means you have n coordinates, you have n momenta, and the time derivatives of the coordinates and momenta are given by partial derivatives of the Hamiltonian. This is something that you learn in a course on mechanics. The Hamiltonian's a function of these q's and p's, and sometimes of the time. Although we like to avoid cases where the time is involved. Then if you take the derivative, time derivative of any function, you get the partial derivative plus the change in f due to the changes of the q's and p's, and then if you use Hamilton's equations, that gets into this expression. And this thing, this sum is called the Poisson bracket, named because after Poisson. And in quantum mechanics, I'm not going to do quantum mechanics, I'm going to stay classical, but it's important to, I think, just for, it's important for me to tell you that in quantum, well, as you probably know, that in quantum mechanics, the function f and the Hamiltonian h become operators, and their Poisson bracket is replaced by the commutator divided by IH bar. So in other words, the Poisson bracket turns into what we call a commutator, which is just the product of the operators in opposite order, the difference of the product of the operators in opposite order divided by IH bar. By the way, let me just make one comment on the seminar. There's just one thing that I think it's possible students could get the wrong impression. In quantum mechanics and quantum field theory, you always add on amplitudes. In the case of fermions, the fermions bring in minus signs, but you still add amplitudes. It's just that the minus sign creeps in. Okay. Sorry about the okay. I just can't break myself of that stupid habit. Now, whoa. So we've got different kinds of Hamilton systems. The kind that we really like, and which, you know, in courses on mechanics, this is what's emphasized, is you have n symmetries and n conserved quantities, and you imagine the time translation invariance is one of the symmetries, and that the Hamiltonian and the conserved quantities are time independent. In this case, we say the system is autonomous, and the Hamiltonian is one of the conserved quantities, and its Poisson bracket with each of the conserved quantities vanishes. And if moreover the conserved quantities have vanishing Poisson brackets among themselves, then they're said to be in involution. And the bottom line after all this wind-up is that an autonomous Hamilton system of degree n that has n independent conserved quantities that are in involution is said to be Liouville integrable, and what that means is that one can, in principle, integrate the system. And in a mechanics course, you typically get the impression that this is the common case, this is the standard case, and so forth. In fact, the opposite is true. This is extremely rare. And in nature never occurs, and but there are cases where it almost occurs. So if you have, for example, if you imagine that this, that you have planets moving around the sun and the planets don't interact with each other, well, then you have a Hamilton system. I mean, a system that's Liouville integrable. Another example is harmonic oscillators. If you have a bunch of if you have n harmonic oscillators that don't interact, then they obey very simple Hamilton equations that are independent of each other. And the energy of each oscillator is conserved, the coordinates vary in this way, the momenta vary that way. These variables, the q's and the p's, run over the surface of an n-dimensional surface of an n-torus in a phase space of 2n dimensions. And for such a system, the areas or volumes in phase space are conserved as the system evolves in time, and it's all very simple. On the other hand, few systems, as I said, are integrable. And for example, two coupled harmonic oscillators. So you take the system I just said n equals 2, but put in a coupling term and a quartic term. You get the complicated dependence that is shown in this figure. The second image is blurry. It's sharp on the computer screen, but it's not very good on the projected image. So these are the coordinates of the first harmonic oscillator for time going from 0 to 100 on the left and 0 to 500 on the right. The initial conditions were the q is equal to 0, the p is equal to 1, m is 1. The frequencies are different, and lambda was half. So, I mean, I think I wrote Matlab code to generate these figures and just vary the parameters until I got something that looked interesting. You still get candy if you ask questions. Anybody have a question? All right, let's look at the two-body problem for a second. So two interacting particles moving in empty three-dimensional space. They're a system of what? Well, it's 6 degrees of freedom. The position of the positions of the position of each particle is 3 degrees of freedom, and then there are 2 particles. So that's 6. There are 7 conserved quantities: the energy, the total momentum, and the total angular momentum. These are in involution, they are independent. The system is Liouville integrable. Its motion is ordered, and if bounded, it lies on the surface of a 6 torus. Or maybe it's a 12 torus, actually. But anyway, it's some sort of very orderly thing. But as I said before, integrable systems are very rare, and even though Hamilton systems are special, remember, the Hamilton system is one where the momenta and the positions, the coordinates and the momenta vary by means of according to Hamilton's equation. So that already is special. And one aspect of that as being special is they have these funny relations, and these phase-space volumes over a closed trajectory, it's time independent. This is called a Poincare invariant. And so areas or volumes of space are constant in time. along the trajectories. On the other hand, even though Hamilton systems are very special, they are, few of them are integrable, and in particular the two harmonic oscillators that were interacting, that's not an integrable system. And moreover here, if you have three interacting particles, say interacting gravitationally, moving in empty space, it's a system of 9 degrees of freedom, but only 7 independent conserved quantities. This is called the three-body problem, and it is non-integrable. And as far as I know, it's just, nobody's solved the three-body problem. As far as I know, I haven't worked in the field, but as far as I know, it's one of the many embarrassing things in physics that we don't mention very often. Systems, general systems, well, let me just say an autonomous system of n first-order ordinary differential equations look like this. And it has a very nice form. x1 dot is f1 of all the x's, down to xn dot is fn of all the x's. And at first you might say, well, this is very, very special. But in fact, it's much more general than it looks. In particular, suppose you have a non-autonomous system, so there are times in the f's. Well, what you can do is you can just set time equal to the n plus 1 coordinate, and then you set fn plus 1. What would that be? That would be the time derivative of the time. Well, that's 1. So you set this equal to 1. And then you've written a non-autonomous system as an autonomous system. Moreover, you might say, well, this is all first order, but you can take a system of n higher order ordinary differential equations. By the way, these are said to be ordinary because they don't have partial derivatives in them. It is so hard to associate the screen with the... Okay, so what is sort of hidden by the projector and the screen and so forth is that if you have a higher order autonomous, or a higher order system of differential equations, ordinary differential equations, you can still write it as an autonomous first order system. What you do is you add more than n first order ordinary differential equations. And one example of this is something called the Van der Pol oscillator, which was a big deal, I think, back in the 20s or 30s. It's a second order time-independent differential equation. Oh, I will put or have put these notes on the class webpage. I don't think I got around to it, but I may have. Anyway, it's a second order differential equation. It's time-independent. No, it's time-dependent. And it's time-dependent because of this sine omega t term. And it describes a forced Van der Pol oscillator, and forced, this is the forcing term. If you want to turn it into an autonomous first order system, what you do is you set x1 equal to y dot. So that's the trick. You set s1 equal to y dot, and then you set x2 equal to y, and you set x3 equal to t. And then bingo, it's a first order autonomous system. x1 is x2, and so forth. x2 dot is x1. That's because x2 dot is y dot, and y dot is x1. And x3 is t, so x3 dot is 1. So that's your system. And, but
by the way, Matlab makes it very easy to integrate these equations, systems equations like this. And I'll show you the Matlab code momentarily for one of these, or two of them maybe. And if one of you wants to do a project, I would encourage you, since Matlab is available free of charge here, to play with systems of ordinary differential equations and make fun graphs. You can, I mean, it's just amazing what Matlab with modern computers can do, integrating these things. And I imagine if you start out doing this, the first half hour or hour will be frustrating because you need to get Matlab to do what you want it to do and so forth. But once you get the knack of having Matlab solve these things, you I think can have a great deal of fun. Anyway, this exhibits chaos for certain values of the parameters, mu, a, and omega. The unforced oscillator, when you set this term equal to 0, has trajectories that converge to limit cycles, as shown in figure. The figure is here. And what's going on with this limit cycle is here we're starting out at the origin, and it goes out, but then as time goes to infinity, it just describes that oval. It goes around it converges to a line, and that's a limit cycle. Moreover, if you start outside this limit cycle, the scales here are different. Outside the limit cycle, it spirals in and then converges to the same limit cycle. That thing is called an attractor. So, in other words, if the motion of the system converges to a certain path, that's called an attractor. And in this particular case, this was the unforced oscillator, and well, I don't think those details are very important.
So by the unforced oscillator, you just take away the sine component there?
Yeah, this was the unforced, so A was 0.
Okay.
Or you can set omega to 0. Okay, so I was mentioning attractors, and Hamilton systems, remember, evolve in ways that conserve their areas in phase space. But arbitrary autonomous systems behave more generally, and the phase space areas of some of them, ones we call dissipative, so they're losing energy in some way, or something equivalent to energy. There, the phase space areas typically shrink, and if they converge to a point or a set of points, that's called an attractor. And an attractor may be a point that has dimension 0, it may be a loop, or a limit cycle, which is called a limit cycle. Then it would have dimension 1, but it can be more general than that. Namely, it can be a surface of integral dimension, or it can be a fractal, which is a set whose dimension is not an integer. And somebody in the field of modern mechanics was clever enough to call fractal attractor a strange attractor. And that, I think, just the choice of that word, strange, modifying attractor, I think that gave the field, created a great deal of interest in the field, the idea that you had a strange attractor. Anyway, one of the most talked about examples of chaotic systems is one that was invented by Lorentz, who was actually actually studying weather, I think. Not weather in the sense of probability, but weather in the sense of snow and rain and so forth. And the system that bears his name is three first-order differential equations. And the first one is linear. The second one is not linear because of the xz term. And the third one is also not linear because of the xy term. And this is so famous that the various constants are called the Prandtl number, sigma, the Rayleigh number R, and the parameter B, and they're all positive. Here's the Matlab code, and you see how simple it is. So Matlab just is just very easy to use for this particular application. So this is the initial condition. T-span is just how long you're going to, how far you want it to integrate, starting at 0, how far you want to go in time. So this is of time from 0 to 300. And then the particular syntax is Tx equals ODE 45. That means you're going to use a particular program. You're going to ask Matlab to use one of its programs, ODE 45, to integrate the system of differential equations. And then what you say is at Lorentz T-span, and then from the initial condition 0, and then you tell it to plot. In this case, for all the time case, all values of the time in T-span, you're going to plot x1 and x3, which is to say x and z. And then what's the function? Well, the function is x prime is equal to Lorentz of t and x. These are just definitions of the parameters. And then x prime is just Matlab format or syntax for these three differential equations. So this is x dot is, I call sigma s, x of 1, plus s x of 2. So that's because we're dealing like that. Then y dot is this, that's translated into that. The semicolon is used to separate statements. So this is like that's the first equation. The second equation is there, and then the semicolon gives you the third equation, c dot is equal to that. And then you just say end, and boom, it generates that plot. The plot was on the next page. The initial conditions here are x and z equal to 0, y equal to 8. And this is...
Quick question. So is that were you defining the Lorentz equation in that, or was that something already built into Matlab?
I was defining it here. I don't think it's...
Okay.
I mean, it might already be built into Lyapunov.
Yeah, the syntax was not quite what I was used to, so it's just... yeah, it's good. It's fine.
All right, so I think, in other words, I think that by doing it this way, I could have made this squared or cubed or something.
Yeah.
Would have gotten a different figure, but Matlab would have done it correctly.
Yeah.
Okay. All right, so let's look at what it actually does. And this is the famous Lorentz butterfly. Let me just pull it down a tad. Well, I think I'm going to put it up a tad so as to be able to read the bottom part. So this is what you get. It looks better on a computer screen than on this projector. And this is the trajectory of the particular Lorentz system for T-span 0 to 300. And now you might say, well, what is this thing here? Here I've just gone from 0 to 300. If I had wanted to display the attractor, I would have gone from, say, 10,000 to 1,000,000 or something, but then we would have gotten just sort of something that would have looked like a black butterfly, or, I mean, the resolution of the projector, and for that matter of the resolution you get when you plot a figure, just wouldn't be satisfactory. And the attractor, it turns out to be, it's of dimension 2.06215 with, I guess, continuing digits that I don't write down. So this is called a strange attractor. In other words, in three-dimensional space, x, y, z, what we're plotting here are x and z. This, the trajectory of the curve in three-dimensional space eventually converges at infinite time to a set of points that has dimension slightly bigger than 2, but not as big as 3. So it's not a solid, it's something in between, and it's a particular fractal. Any questions? I'll say more about fractals in a moment and how you compute dimensions in a moment. But.
So what exactly do you mean by dimension?
What exactly what?
What do you mean by dimension?
Well, that's of course the key question, and I now owe you at least 2 candies. So here's one.
Okay.
And there's the other one. It's a good thing I'm not giving out eggs. I'll get to that in a moment. There are several definitions of dimension, and for most systems they coincide. They're just different ways of defining dimension. But we'll get to that in a moment. Let's see what. Okay, there's another system here that I made a plot of. This is called the Restlessness system. This is 3 differential equations. Once again, only one of them, in this case, only one of them is nonlinear, and they illustrate limit cycles in a somewhat simpler way. So here, there was a parameter there called C. Where's C? Let's go back and see what C was. Okay, you see, C is just a very innocent parameter. It's just sitting there. And the graphs that I showed you briefly and will show you again have A equal to B to the point 2. Initial conditions, everybody's 0. And there's a simple limit cycle for C equal to, a period 2 limit cycle for C equal to 3, period 4 for C equal to 4, period 8 for C equal to 4.15, and then it becomes a strange attractor when C is 5.7. So let me show you that again. Of course, I can't show you the strange attractor really because if I let this go, it would just go essentially black on us. But there you see that you have here 2 loops. Here you have 4 loops, 8 loops, and then eventually a strange attractor there. And I suppose the dimension of the thing is here. It's slightly greater than 2. And so this again, it's a curve. In other words, this system for C equal to 5.7, you integrate out to very large times, let time go to infinity, and then it starts, runs over a surface that has a dimension slightly greater than 2. So it's not a solid three-dimensional object, but it's more than a two-dimensional object. Now let's see, what did I skip here? Oh yes, quite a bit. All right. So that was the Restless system. Chaos. Well, Henri Poincaré studied early in the last century the three-body problem and found very complicated orbits. Mind you, he was doing this basically with his mind and his fingers. He didn't have calculating machines, let alone computers. And what he found was that after a transient period, classical motion settles down to 4 possible forms. One is periodic, and in this case it's sometimes a limit cycle, steady, damped, or even stopped. Third possibility is quasi-periodic, so there are two or more frequencies, and then finally chaotic. Now, chaos, there's no single definition that I know of chaos. It takes different forms in different systems, and what's characteristic of most of them is extreme sensitivity to initial conditions. And so typically what you have is you might have 2 trajectories that start from slightly different points and then evolve such that the distance between the two, I'm a little puzzled as to why I have 3 lines here. But anyway, it evolves exponentially. And this lambda, this coefficient of the exponent, that's called a Lyapunov exponent. And in a serious course on chaos, you find that people can show that a first-order autonomous dynamical system can be chaotic only if it has a dimension of 3 or more. And the driven damped pendulum, the Lorentz system, and the Restless system all have n equals 3 and evolve chaotically with certain values of the parameters. Here are some more examples. Duffing's example, and here what you have is you attach a thin piece of iron to the end of a rod, and the rod moves sinusoidally in the x direction at a certain frequency, but it's near 2 magnets, and then the x coordinate is described by the force Duffing equation, force because of the right-hand side, and it looks like this, and it varies chaotically to suitable values of the parameters. So let's see, I think I can draw you what you imagine. So you've got this thin piece of iron that's down here, and then you've got 2 magnets here, or a magnet. You've got a positive pole here, a negative pole, and actually I wrote it as plus and minus. If you have plus and plus, it might also behave in a similar way. But and then this thing is going back and forth sinusoidally. And when it gets over here, the thing swings over this way, and then it swings over that way because the iron's attracted to the magnets. Another example that has driven some people crazy late at night is drops from a slowly dripping faucet. I guess the standard of living in this country has risen to such an extent that this is rarely an issue. But when I was young, I was bothered by some tripping forces in one situation. I don't remember what it was. Anyway, if the faucet is dripping very slowly, then the drops fall at constant intervals. So it goes drop, 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 drop. But if you then increase the flow slightly, you then find that the intervals are different in alternate in length in the period 2 sequence. So you have one time, the time between the first and the second drop is one interval, but between the second and third is a different interval, but between first and second is one interval, second and third, different interval, third and fourth is back to the interval between 1 and 2. On the other hand, as you turn it to a higher flow rate, you may get period 3, period 4, and at some point you just get no regularity at all. And then there's another famous example, which is Rayleigh-Bernard convection. And this is a fluid in a gravitational field above a hot plate and below a cold plate. And there, if the temperature difference, T is temperature now, if the temperature difference is small enough, then you have a steady convective flow. But when the temperature difference gets big enough, you get chaotic boiling. And so what you've got here is cold, hot, and if the temperature difference isn't much, then what you've got is you've got the water, the hot water going up like that there, and then it comes down over here, and this is the steady convective cellular flow, and so these are the cells. But when the temperature difference gets high enough, then you get something chaotic. And of course, this is basically what is involved with weather on this planet, because the diameter of the Earth is so huge compared to the height of the atmosphere, or effective height of the atmosphere. And the sunlight warms the surface of the Earth, and then the fluid, in this case, is air, but up here it's cold, there it's hot, and so you have this Rayleigh-Bernard effect. But if it gets too hot, then you start having weather, and with global warming, you then get more and more storms. And one of the physicists in this department, or associated with this department, Marvin, I can't remember his last name, he's an expert in lightning, and because of global warming, there's more lightning, and he has made a lot of money advising people in Singapore what to do about lightning, and it turns out that it's a serious health risk, actually. You know, normally we say winning the lottery is like being struck by lightning, and similar odds. Well, in Singapore now, it's no joke. The chance of being struck by lightning and killed by lightning is non-trivial now because of global warming. And somebody who was doing research up in Alaska said that the natives up there had never heard thunder until maybe 10 years ago. Because of global warming, now you have more chaotic weather patterns.
Why is Singapore?
Why what?
Singapore. Why is lightning such a problem in Singapore?
Well, because of global warming. I mean, you know, the chaotic.
Yeah, I was just wondering why that location in particular.
Oh, it's just that in Singapore they have enough money to pay Marvin to go down there and give him advice. everywhere near the equator and especially near the ocean.
Okay.
Okay, because if you're in a place that's, I imagine that's totally dry, really far from, well, I don't know, New Mexico is far from the ocean, and yet we get a lot of lightning. We get lightning here.
Yeah, there's the whole lightning lab down at Tech.
What's that?
There's the whole lightning study lab down at Tech. Like
Down at New Mexico Tech?
Yeah.
I see. Well, anyway, I hope they're aware of Greg Taylor's array.
I'm sure they are.
Okay, because he sees lightning on his array. Anyway,
They're located around that same area. Like
yeah, you're absolutely right. So how
They're
could
just
how could
up
they
on-
miss it?
I also had another quick question.
Yeah. All right, hold on.
No, I don't need more.
All right.
This is one.
Oh gosh. So what exactly makes a system chaotic? Like what defines whether or not it is chaotic? Was it that
Well,
exponential
as
I
a-
said earlier?
Well, as I said in the text here, there's no single definition that fits everything. But the poor man's definition of chaos is that that you have extreme sensitivity to initial conditions.
Okay.
And so you start the dynamical system out in two different states, and then after a reasonable length of time, they're wildly separated. Whereas if you have, for example, those harmonic oscillators that are independent and not interacting, well, they just go over the surface of the torus. And the torus, if you have a fixed torus, you can't, no point can get exponentially far from any other point because they have to stay on the torus.
Mm-hmm.
So, but, all right, so anyway, maps, okay. This is one of the things that Poincaré introduced as a way of visualizing dynamical systems. You can imagine that you have a system in n dimensions, but then if you are just asking when the point in phase space, in n-dimensional phase space, labeling the state of the system crosses a particular surface, then that's a system in n-1 dimensions. And so it's simpler to analyze, and moreover, there's something else about it. It creates a map, and in fact, it's an invertible map. That is to say, xj, xj plus 1, xj plus 2, these are the locations in phase space of the system when it crosses a certain surface. And that's called a Poincaré map. And as I said, it's invertible because you just have these xj, xj plus 1, and to invert the map, you go xj plus 1 down to xj, and then xj minus 1. And consequently, it can only be chaotic if it has at least 2 dimensions, but then, of course, it comes from a dynamical system that has at least 3 dimensions, which is the condition that is necessary for chaos. On the other hand, if the map is not invertible, it can even be one-dimensional and be chaotic. And so now I'm going to show you some quite remarkable examples of one-dimensional chaos. Actually, let me just give you a formula, a particular formula for the Lyapunov exponent of a smooth one-dimensional map. It's 1 over j going to be the logs of absolute values of derivatives, and you take the average of the first j of them, and
if you have a bounded sequence with a positive Lyapunov exponent that doesn't converge to a periodic sequence, then it's chaotic. And that's a book by Allygood, and the book of Allygood, by Allygood and somebody else, I forget. Other aspects of chaos lead, of course, to other definitions. So notice what's going on here. You've got a bounded sequence, and yet the sequences are diverging from each other in such a way that that it has a positive, they're diverging exponentially, which is what positively Lyapunov exponent means. And, well, one possibility is they could be periodic, but if they're not periodic, then they're automatically chaotic. I see that I said something wrong a little while ago when I said, well, you're on a torus, you can't get infinitely far away. The deal, I think, is that with the Lyapunov exponent, you see, even if you were in a bounded sequence, if you shrink the difference in the starting point sufficiently, you can get exponential divergence even though you're in a bounded region. So that's why I shouldn't have said, well, you're on a torus, what can go wrong? So you could have chaos on a torus also. Okay. Anyway, let's go on. There's another example. I'm a little puzzled as to how come I'm only getting to it now. The angle theta of a sinusoidally driven damped pendulum obeys a certain differential equation. You can put it in autonomous form. Again, it's second order, but you make it a first order autonomous system like that. And if you then imagine what the so this then is a system of 3 dimensions, and you can imagine a Poincare map of it, and this turns out to be a strange attractor, and it's actually quite an interesting looking. So this is the Poincare map of a damped driven pendulum. This is theta dot, and so let me read the thing here. It says the first million crossings of the surface at x3 to a 0, and then mod 2 pi. So you have this thing, if the thing goes over the top and so forth, then 2 pi, then you go more than 2 pi. So everything's mod 2 pi. And the particular f is 2.7p, 0.22. And these points form what's called a Cantor Set like strange attractor, and the dimension is 1.38. And the initial conditions were everything 0. As I say, you can have a lot of fun playing with these things. All right, let me just skip to the logistic map. This, of course, is the most famous example because it's so much simpler than all the others. It's just a map. But it's a model that's kind of interesting because it can, to some extent, describe a population of animals with a limited food supply. So, in other words,
if the change in population from xj to xj plus 1 can go down if xj is too big because you've got too many animals eating a limited amount of food, and so the population can go back down. Now, if you wanted to invert this and solve for xj in terms of xj plus 1, well, you've got a quadratic equation, you've got two solutions, so the thing is not invertible. So that's why you can have chaos in this system, even though it's a one-dimensional map, one-dimensional system. And so for r between 0 and 1, the sequences, if they start between 0 and 1, the sequence converges to 0. And that's an attractor then. On the other hand, the attractor, if you set r equal to 1, then the attractor starts to get bigger. It's no longer 0, and it starts to get bigger, and it reaches 2/3 when r is 3. And then at 2/3, it splits into two attractors. And then at 1 plus root 6, it splits into 4 attractors. And at this number, it splits again. And at R4, it splits yet again. And then by the time it gets to here, about 3.57, the attractors have split an infinite number of times. And as R passes 3.57, which is called R infinity, you get attractors that have split an infinite number of times, and chaos appears in increasingly obvious forms as R goes beyond R infinity. There's no reason why you have to stop there. And at 3.8, two sequences that start at 0.2 and 0.20001 differ after only 19 iterations by seemingly random. About the yellow line. Sorry about that. For example, at 21, the difference is 0.2. At 23, it's 0.6. At 74, it's 0.7, and so forth. So that's an aspect of the chaos. At r equal to 4, the logistic map is totally chaotic. What totally chaotic means, I'm not quite sure, but intuitively it's obvious what that means. And then it's equivalent to the tent map. And the tent map is something very simple. It's 1 minus 2. Xj plus 1 is 1 minus 2, xj minus 1. And if you just work that out a few times with your figures, you can see that the sequence becomes essentially almost random. The 2x modulo 1 map also is similarly chaotic. So xj plus 1 is 2xj mod 1. Now, what I should have shown you was the graph, and I didn't show it to you because it is on. All right, so there's the logistic map, and you see that the attractor is 0 for r less than 1, but then you go all the way to 3, and this attractor just rises. But then beyond 3, at 3 it splits, and then it splits again here, and then R infinity is, I don't know, somewhere in there, 3.57 roughly. And these are points. I think I made this with Matlab again, from n going from 29,990 to 30,000, 10 random starting points for R, and between 0 and 1, and R is between 1/2 and 4, and from R equal to 1 to 3, this is just what we were saying before. It's at 2/3 here. All right, let's see. I had to skip forward. Where was the text was?
Okay, we did that. Okay, there's another map. This one is something that I examined just, in fact, what I did was I worked this example out thinking it was the logistic map. It was a sign. It's a sign difference. And so let's examine what this looks like. This one also has a sort of biological interpretation, namely, since reproduction requires two animals, the rate of change is quadratic in the population. But on the other hand, there's also a certain death rate. So this doesn't involve food, it's more just the basic biology. This might have to do with not bacteria, some sort of animals where there's plenty of food, I guess. And it describes, well, as I said, for R less than 1, the attractor again is 0. It splits at R equal to 1 into 2 attractors. At root 2, it splits again. And chaos starts around 1.57. I say around because this is something I've worked on, and I did not search the literature to find it. So this is the population map. So this is the other thing. This isn't the logistic map. This is the population map. And I guess it's animals with plenty of food. And I don't quite know why they would follow this trajectory, but you can see that after somewhere in here, it becomes obviously chaotic. Okay, let's see where the text ended. Right. Okay, here's another example of chaos. This is the simplest map of chaos, and it's due to Bernoulli. And you take as the initial point some arbitrary number between 0 and 1, and then you write it as a binary decimal. And a binary decimal, of course, is you write it as 1 over 2 to the k, and then there's ak. These coefficients ak. And what you do is you drop off. You just get rid of A1, and then get rid of A2, then get rid of A3, and get rid of A4. And so X1 is this, X2 is that, X3 is that. And so you can see that if the number X is a real number as opposed to a rational number, then this thing roams uncontrollably and chaotically. And ergodically, apparently, over the whole sequence. Can I borrow your pen or a pen? Okay, just for a second. I wanted to, something occurred to me and I looked to fix. Any questions? Okay, then there's Anand's map. This is a two-dimensional map. So this is again a map as opposed to an autonomous system. Although it might be, it may be that this, an autonomous system crossing a surface. In other words, it might be a three-dimensional system, and here we're giving the XY coordinates when it crosses a certain plane, a certain value of Z, say. I don't know if that's the case for this particular example. If B excuse me, if B is not equal to 0, then it actually is invertible, but it's two-dimensional. If you said F equal to A minus J squared, then it's called a nonce map. And if A is 1.4 and B is 0.3, then it's chaotic and it converges to a certain attractor. So let's see where that attractor is. Goodness, where the hell is that attractor? My goodness, what? What's going on? What? It may be that I did not. Maybe I dropped the attractor from the chapter. So, what I had a pen. It says figure 1710. 8. Well, there it is. It's way at the end here. That's one of the problems with LaTeX. It's very hard to control where the figures go.
You just put lots of exclamation points after.
My goodness, look where it went. Ridiculous. Do you have a way of controlling where they go?
Oh, I mean, it's not great, but when you put H for when you put a figure to designate that it's here, and then you can put exclamation point after it to tell it, no, really, right here.
Oh, really?
It doesn't always listen to you, because it really doesn't like putting images where you want them. But
Yeah. All right. Well, great. I've got to try that. I didn't know about that.
yeah, it's H and exclamation
Yeah. Well, I've got to do something. Actually, I'm not nuts about this figure. I don't think it's a particularly good figure. I think the other one that was is more interesting. So this is the first 10 to the 4th points of the strange attractor in those maps.
That's all right. You'll figure it out.
What? What'd you say?
I said you'll figure it out.
All right. All right, let's see where we were here. All right, I think the next time, let me just see if yeah, all right, good.
Stop looking at me. Be proud of me. You're getting a 0 on your paper.
All right, anyway. Now, finally, I'm going to answer your question that was asked at the very beginning. A fractal set has a dimension that is not an integer. How can that be? And Hausdorff and Besikovich showed how to define the dimension of a weird set of points. And what they did was they introduced what's called a box counting dimension. I think this is the easiest way to think about this. This is something that was mentioned, by the way, in a colloquium by, her name is Jane Brown. She's
Kate Brown.
Huh?
Kate Brown.
Kate Brown. Was talking about. Anyway. So here's the box counting dimension. What you do is you cover the set with line segments if it's a one-dimensional set, or if it can fit in one dimension. If it fits in 2 dimensions, you cover it with squares. If it fits in 3 dimensions, you cover it with cubes. Or you cover it in general with n-dimensional boxes of psi epsilon. And if you need n of epsilon boxes, then what you do is you take the ratio of the log of n divided by the log of 1 over epsilon, and you take the limit as the size of these boxes goes to 0. And that's the box counting dimension. And An example of that is the dimension of the Cantor set. Now the Cantor set, I had a lot of trouble making that figure, and I would love to know of a cute way of making a better figure than that. But anyway, this is the first 5 approximations to the Cantor set. So the Cantor set is basically you take first the interval 0 to 1, and then you knock out the middle third. Then you take those two, you take what's left and you knock out the 2 middle thirds. Then you take what's left and you knock out the 4 middle thirds and so forth. And then in the limit of n going to infinity, that's the Cantor set. So what you can do is you can cover the interval by b minus a over epsilon line segments of, well, first of all, I've skipped here because I saw the figure I talked about the Cantor set. Let's just look at the definition of the box counting dimension. If you can cover the interval with this many line segments, then what's the dimension? Well, it's b minus a over epsilon divided by log of 1 over epsilon, and then working out that what the log is, this is log of b minus a minus the log of epsilon, and the logs of epsilon cancel, and then you just have this, and as epsilon goes to 0, this goes to 0, and this goes to 1. So in other words, if it is, so the dimension of the interval from A to B is, of course, 1. It's one-dimensional. On the other hand, if you apply this to the Cantor set, then what do you get? Well, you can cover the nth dimension with 2 to the n line segments, but each segment is of length 1 over 3 to the n. And so then the fractal dimension is log of 2 to the n divided by log of 3 to the n, but that's, you bring out the n log 2, n log 3, n cancels, you get log 2 over log 3. And so it's obviously not an integer, in fact it's not even a rational number. Another example is the Koch Snowflake, and the construction is on the next page. Maybe I can flip to the page. So what you do is you start out with a triangle, and then you take each side of the triangle and replace the middle third by another triangle, and then you iterate that process, and pretty soon you get something that, frankly, doesn't look like a snowflake to me, but that's what it's called. And what's the length of the thing? Well, with each step, there are 4 times as many line segments, but each one is 3 times smaller. And so the length of the curve is 4 over 3 to the n. And it grows without limit as n goes to infinity. So in other words, it has dimension greater than 1. And if you then ask, well, how big is it? Well, it's 4 to the n divided by 3 to the n of logs. That's log of 4 over log of 3. And you get 1.26. There's another dimension, another definition of dimension, closely related. This is called the self-similar dimension. You consider the number of self-similar structures of linear size x needed to cover the figure after n steps and take the limit. Well, it seems to me this is almost the same thing. And you wind up in this case with 1.26. Isn't that the same? That must be the same number, isn't it? Yeah, it's the same number. Right, which is equal to its box kind of box counting dimension. There are other dimensions of a set. There's a correlation dimension, there's a Kaplan-York dimension. And the advantage of these is that these are easier to measure in some cases. Obviously, the Hausdorff box counting dimension is pretty straightforward if you're dealing with one-dimensional structures. But you can imagine that more generally you have trouble with that. So attractors of strange fractal dimension are called strange. Lorentz butterfly is an example. It has Kaplan-York dimension of 2.06. The loops of the lossless system are a strange attractor dimension 2.01. The damp-driven pendulum has a dimension 1.38. Anon's map is 1.26. Chaotic systems often have strange attractors, but chaotic systems can have non-fractal attractors, and non-chaotic systems can have strange attractors. So we managed to get through the whole thing, actually. There are various books on this sort of thing. Two that are pretty good are one by Strogatz, and I would recommend the first edition because it was nicely published. They came out with a second edition, and they shrunk the size of the book by essentially a factor of 2, making it cheap to produce, but it's almost impossible to read because the inner margins are essentially 0, and if you open the book wide enough to be able to read it, you crack the binding. So it's really annoying the way some publishers take advantage of readers. There's another book called Chaos, an Introduction to Dynamical Systems by Alligood et al. That's these are two very well-known books, and then there's some other one that actually I don't know much about it at all. I think we're out of time now, so we ought to stop. Does anybody have a question before we turn off the camera? Assuming that it's been on. Question? No. All right, so let's turn it off.